Thanks for coming, everybody. This is going to be a very rapid run through of a lot of information. I appreciate that. First of all, introductions. My name's Richard Barry. Our company is Real Time Engineers Limited, and I am the original founder of the FreeRTOS project. And now we carry on developing, maintaining, supporting, and promoting FreeRTOS. There is a suite of products. So FreeRTOS is the main product we're talking about today. To make you aware, there is also a commercial version which is provided by a third party and a safety critical version as well. I'll talk a little bit more about that when we come on to the value proposition here. The agenda for today, what we're not going to do, I'm afraid, is tell you what an operating system is or a real-time kernel is per se. I have to assume that you know that already. What we're going to be looking at is how you can use it with the LPCOpen drivers. So we're going to start by saying what is LPCOpen. Again, hopefully you're aware of that already, so we're not going to dwell on that. We're not going to say what an RTOS is, but I am going to tell you what FreeRTOS is. That won't describe how kernels work or anything like that, just the market and the positioning for FreeRTOS itself. And then we're going to look at what are the advantages of using an operating system, because you don't always have to use an operating system, but at some point you start to get advantages. And normally in a talk, I would go through verbally what the advantages are, and it's a little bit abstract. So what we're going to do in the second half today is actually do a demonstration and try and show you with some diagrams and live demonstrations some of the benefits you can get. So we will use LPCOpen without the RTOS, and then we'll use it with the RTOS as well and show you what the differences are. So we'll start with LPCOpen. Well, what is it? It's lots of things. It's drivers, chip support at the bottom here, so peripherals and the actual core itself. And then board support packages for, today we're using something from, I'm demonstrating using a board from NGX. So those are board support packages for various off-the-shelf boards you can use, and then middleware as well. And on top of that, you have pre-configured projects as well that use all this software. So the idea is you can just download this from NXP, get one of these boards and get up and running very, very quickly with all the peripheral drivers and that sort of thing. Now included in there is the RTOS as well. And we're going to actually look at all this stuff, demonstrate it, okay. So obviously the benefits of LPCOpen, well, I think I've mentioned them already. It's cross all the LPC microcontrollers in the classes supported. Get up and running very, very quickly. It's all tried code, tested code for you. Again, this is just a diagram showing the same thing really, the chip layer, board layer, the middleware components. The reason I've got this diagram up is that one of the things we are going to be using here is the USB code. So the drivers for the USB code are in LPCOpen. And one of the very nice things about the chip we're using today is the drivers are actually in the ROM. So it doesn't take up any of your flash space, and we're going to be using a virtual COM port using the LPCOpen driver and the ROM'd code. Again, we'll demonstrate that very quickly, very soon rather. So how do you get LPCOpen? Well, there's the URL, LPCOpen. lpcopen.com/LPCOpen will take you to the main landing page, and from there you can click a link and be taken to sub-pages or sublinks for all the supported architectures, and then you click on one of those and it will take you to pages for that architecture on different hardware platforms. And the platform we're using today, like I say, is the NGX. So I should say that LPCOpen, you can use it with the Kyle tools, the IAR tools, or the GCC LPC Expresso tools. So the LPC Expresso is what we are using today, which is an Eclipse-based IDE. So when you've downloaded your code, you can just import into Eclipse all the projects. So this is the sort of thing you'd expect to see. There are a lot more than this. You can see the scroll bar here. There's a lot more than this. This is just to demonstrate. So this is exactly what we're using today. And in here, there are core, see there's the library which supports everything on the chip, and there's another library which supports everything on the board, does things like mapping LEDs, to take a very basic example, onto that particular hardware. And then we'll be using some of the middleware stuff as well. So when we come onto the live demo, I'll be using this exact code here, but we will just choose 4 or 5 of those projects rather than importing all of them. I've imported them all in for you already because it takes too long otherwise. I have taken a few shortcuts and things I've prepared. So that's LPCOpen. I'm afraid I did say I was going to go very quickly because we've got lots to get through. So I know I've skimmed over what is really a talk in its own right. So FreeRTOS, just to define, different people's concepts of what an RTOS are really depend on whether you're coming from a very small microcontroller world or coming from a much bigger applications processor world. So in the applications processor world, really an RTOS is represented by this bigger all-encompassing circle here. And you might expect file systems in there, TCP/IP, security mechanisms, all that sort of thing. That's all part of the RTOS. All RTOSes have a scheduler at their heart, the thing that decides which task or thread is going to run at any particular time. Well, FreeRTOS is sort of halfway in between the two. It's what I'd call an executive. Of course, it's got a scheduler, and there are file systems and TCP and that sort of thing that will work with it. As a package in its own right, it has inter-task communication mechanisms and timers and that sort of thing. So it's a little bit more than the scheduler. And the sort of woolly word we use for it would be an executive. These phrases and words are not defined anywhere, so which is why I try and define what I mean by it. When we come to the demonstration, we're going to be looking at diagrams like this. So rather than explain it during the demonstration, I'll try and explain it a little bit now. Hopefully it's fairly obvious. So we have different threads of execution running here. In FreeRTOS, we call them tasks because thread can mean something a bit more specific to people from, say, the Linux world or something like that. We'll come to the idle task later. Application tasks are given a priority by the application writer, and the kernel or the scheduler decides which thread or which task is going to run at any particular time. And it does that by looking at the priorities of the tasks and whether they're able to run. So here we have time moving along this axis here, and the colored lines are just showing you which task is running at any particular time. So you can see here at time t9, the task represented by the red line, which is a periodic task in this case, executes. And then at time t11, this higher priority event-driven task, something happens, an interrupt comes in, that task can run, so it preempts the task that was running previously. It does that immediately. This task doesn't know it's happened. It executes the event task until the event's finished its processing, can't do any more processing until another event coming in. So the scheduler then drops back down to the red task, and the red task can then carry on until it's finished, at which time it drops back down to the blue task. So that's the sort of concept of the diagram. In the demonstration, we'll show how using the kernel can make you change that execution pattern and the benefits you'd get from that. So there's another graph just showing where FreeRTOS fits in. Applicability is a kind of, you can't really quantify what that means, but it's just, if it's higher up this axis, it's more applicable. On this axis, you have maybe on this side, very small 4 or 8-bit processors. At this end, your big 64-bit applications type processors. Well, FreeRTOS sort of fits in the middle. So where you've got enough processing power or enough peripherals so that you are writing fairly complex applications, then you're going to start getting a benefit from, at some point there's this crossing point. So at some point it's more beneficial to use a kernel. On the other side of the crossing point, where it's a less powerful processor or a less complex application, you're going to get more benefit by not using a kernel. I should say that FreeRTOS is completely free. I'm not trying to sell you anything here. So I'm quite happy to say that you don't always need to use a kernel. I'm not saying thou shalt use a kernel because I'm going to make lots of money out of you if I tell you that. It actually doesn't make any difference to me. I'm very much wanting you to be able to use the right tools for the job you're doing at that particular time to make the best applications you can. So a little bit about FreeRTOS itself. There's a lot of FUD and misinformation put out about it, so I feel necessary to justify it a little bit. FreeRTOS is provided to you completely free, and you think, great, that's it's a very nice price, but hang on a minute, what about support? Or hang on a minute, what about IP infringement? That's the thing that people get really scared about. I mean, where's the code come from? Do we know that it's not actually owned by someone and we're accidentally stealing it, or all these sort of things? So FreeRTOS itself is developed and managed exactly like a commercial operating system. All the IP is very strictly controlled. We will not ship anything with FreeRTOS that we cannot guarantee is completely clean. It's very well supported, it's very robust, it's, you can just get on the website and see the level of support and the number of applications it gets used in. The FreeRTOS code remains open source, but where this line is supposed to represent the API, so if you have application software that's using it, or you have driver software like LPCOpen that's using it, or you have middleware software like you bought a TCP/IP stack from someone like that, then the license here does not affect that license there at all. Basically, it is the market-leading real-time kernel in its class, and that's borne out by the results of the surveys. 2011, 2012, and 2013, it came top. I think the results this year are being announced tomorrow, and I'm fully expecting it to become top again. It grows every single year. It's used in every application area you can imagine, even sort of aircraft navigation systems, bizarrely. 107,000 downloads last year that we can count. Of course, there are lots that we can't count. For example, every LPCOpen package you download's got FreeRTOS in it. We can't count those. So that's a very, very conservative figure. Coming back again to the licensing a little bit, we like to say that FreeRTOS offers a really, really low risk option for you, because you can take the code, develop your product, take it to market, and we never know anything about it. And you can do all that without paying us anything or even talking to us. Now, at any time, if you do decide that you need a little bit of extra help, or you need a little bit of extra support, or you get to the end of your project and your manager says to you, oh, hang on a minute, who's providing the indemnification for this software? I'm putting this in a product and I'm shipping 10 million products. What happens if there's some comeback on this? Well, you can buy a commercial license, as I mentioned at the beginning of the talk, and the commercial license is very low cost. It's exactly the same source code. You don't need to change anything. The only difference is it comes with a standard commercial license instead of the modified GPL. You get ticketed support, and it's fully indemnified as well. It's got insurances and all that sort of thing. And that's provided by a third party under license from my company. Ecosystem-wise, there is a growing ecosystem. This is just showing a sample of products that are on the FreeRTOS website itself. It's worth showing you these things because quite a few of these things, the command line interface we're using today, some of these things are actually, these are generally dual licensed. So unlike FreeRTOS, these will be pure GPL or commercial. But on NXP microcontrollers, a lot of these you can use for free under the commercial terms. One particularly nice product, which there is a free version of, but obviously the free version is limited, you don't get all the functionality of the trace, is this profiling and tracing and optimization tool called FreeRTOS Plus Trace. very, very nicely shows you the kernel calls that are being made, the tasks that are running at any time, the response times between a task being made, running, and actually running, and all things like that. And you can follow data through here, and you can do all sorts of nice things. It's used actually a lot for optimizing code. The reason I want to highlight this is because today we're doing demonstrations, and I'm going to show you a static snapshot of the execution pattern. If this was a 2-hour talk rather than a 40-minute talk, what I would do is use this tool. We would record the execution pattern and then be able to view it, but time today doesn't really allow that. Okay, so now we're coming on to what are the advantages. So I've said what LPCOpen is very, very quickly. We've assumed we know what an RTOS is. We've said a little bit about the FreeRTOS distribution model and licensing. So we've got these things now. Why would we want to use them? It's all very well saying what they are, but you need some context. So how do you structure your software? Now, again, if this was a longer talk, I would ask people in the audience and we would have a discussion about it. But again, time constraints, I'm just going to suggest that a very common way of organizing your software would be using super loops, using foreground, background processing, so you've got interrupts coming in and that sort of thing. This diagram is supposed to represent that, okay? Here's a piece of functionality, here's a piece of functionality, here's a piece of functionality, and you're going to execute this, go on to the next one. Here's another state machine. Maybe it's service TCP stack or service USB or something like that. It would maintain state, you'd execute that, go on to the next one, and cycle around like that. The question is, though, will it scale? If you're using a small LPC 800 or something like that, not much RAM, not much interfaces, not many interfaces and that sort of thing, you haven't got far you can scale, and it doesn't really matter. If you're using an 1800 part or a 4300 part, and you've got loads of serial interfaces, SPI interfaces, I2C, Ethernet, and this sort of thing, and you're trying to squeeze more and more on as your product evolves over time. Someone decides, well, we used to have USB, but let's put Ethernet on there as well. Or someone says, oh, there's a much faster version of that chip now. Let's change the chip we're using. How does it affect your design here? And these are all points you can debate, okay? There are no absolutes. It's very, very subjective. But I've listed here some of the points that are supposed to highlight why that kind of design is not that scalable. Once you start increasing the size of your application and really the complexity of your application, I'm sure you go to any talk here, people are going to start telling you about how software is becoming more complex every year and how do you manage the complexity and this sort of thing, especially with touchscreen interfaces and Wi-Fi and all these kind of things. It's a lot harder than it used to be. Integration, we'll look at that a little bit. Code reuse, we'll look at that a little bit. Mixed processing requirements, we've looked already event-driven and periodic tasks and that sort of thing. If you change the speed of your hardware, you want things to execute at exactly the same rate, and so on. So the real problem here is an interdependency that you have between the functionality of your system and the execution pattern or the timing of your system. So how can an RTOS alleviate those problems? Well, you can think of writing in C being a higher abstraction than assembler to solve some of these problems. Writing in C++ being a higher abstraction than C to solve some of these problems. You're increasing the modularity the higher up the abstraction you go. Once you start breaking things into tasks, then you're going that extra step again to make things more abstract and more at a higher level. So rather than having one state machine that goes onto another state machine, that goes onto another state machine. You're breaking your state machines up into sequential pieces of code and running them all independently. So rather than in one state machine having to remember state, leaving it and then coming back and loading that state again so you can carry on. State might just be which switch statement you're in at the time. It can just be one variable, but whatever it is. It becomes just a sequential piece of code. Something which is working in the background is just going to be a loop anyway. An event-driven task where you're waiting for the interrupt, but you're not using any CPU time whilst you're waiting. You go to, that task is not available to run, so the scheduler runs something else. So it becomes much simpler code, much simpler to maintain. You can take those autonomous tasks and put them in other applications quite easily. And it's the kernel that actually guarantees to you how they are going to be executing. The timing is all taken care of by the kernel. So if you change the speed of the hardware, but you tell the kernel, I want it to run every 10 milliseconds, it doesn't matter what the speed of the hardware is, it will run at 10 milliseconds anyway. So now, I should have said before, by the way, that the sort of grumpy and ambiguous faces over here were supposed to be bad things, and now what we want to do is use the RTOS to make those grumpy people look a little bit happier, which are these green faces. So again, you can debate these. It's not, there's no absolutes to these things. Different people are going to have different opinions on where the trade-off is in all these things. So when we were looking at super loops, I said the intermingling of your functionality and the timing was the problem. So this is just saying that when you use the RTOS, you're decoupling those two things. So, demonstration. Right. So the first that there is a subset of the projects that I've just imported. Actually, that one at the top is not. That's one I've created myself. That's what we're going to come on to. But everything below there is a subset of the projects which I've just imported from that download I showed you at the beginning. I haven't changed anything, okay? So here we have the chip support. This is the support package for the NGX board, which is just this tiny little board. We've got this virtual COM is the first thing we're going to look at. Now this virtual COM is using let's just get this CDC virtual COM. So this is just using the drivers from LPCOpen that use the drivers which are pre-ROMmed into the chip itself. They're not on the board, the drivers are actually in the chip itself. So what we'll do is we'll run that. And then just to prove it works, we'll come over here, new connection, COM30, and hit enter, and you can see it's connected. It prints out hello world just to show it's connected. I mean, we could look down in the code to see where it does that. And in fact, a bit later you'll see it anyway, because I'm going to edit the code a little bit. And then it's just going to echo all the characters I type in. I have to remember to disconnect it again because it gets confused. Because it's a virtual COM port, when I reset the chip, suddenly the COM port's disappeared. And then it's a problem trying to connect again. So this is an example. So this is an example of running basically a super loop. So this is, in fact, this is all it's doing, is just sitting in a loop and saying, has an interrupt come in from the USB port? Yes, it has. I'll do some processing. And I'm going to spin here again and do nothing. Has an interrupt come in? Yes, it has. I'll do something. So you get this kind of execution pattern. So here's our application code is spinning around doing nothing. ISR interrupt service routine comes in, maybe it's a characters received or something like that, and it processes the interrupt, drops back to the application code, and so it goes on. So that is how a sort of super loop execution pattern would appear. So the next project here we're going to look at, there is a point to this, by the way, because we're going to combine these in a minute, okay? Because I'm not just randomly picking projects to show you. So this one is also, let's start this. This one is also completely unmodified, it's just in the LPCOpen package. And this actually uses FreeRTOS with the lightweight IP to generate basically just a little echo server. So we'll start that running. Now you can see here, this is a FreeRTOS call here. The way it looks on here is quite, it looks more complex than it is. I'll show you a simpler example if there's time at the end, just to show you what that function call is doing. And then it's starting the scheduler, so it's going to run this task basically. And that task then creates other tasks as well. So again, we'll run that, and just to show it's actually doing something. I've turned off the DHCP, by the way, because it's just running on a local point-to-point network here, so I know what the IP address is. And we should find, yeah, so that's just pinging back what's going. So there we have two pieces of functionality, one of which is already using FreeRTOS, so that's nice because we don't have to worry about which files to include or configure it and stuff like that. And then the other piece of functionality is the USB, that's right, CDC driver. Now I'm putting myself in the position of somebody who is looking at this chip and they're looking at LPCOpen and they're thinking, great, I've got two projects now that run, but really I want TCP and I want the virtual COM port because I want to run a little command line interface like that. So what do I do? Well, at the evaluation phase, I'll show you how easy it is now to combine those two together using the operating system. If you actually went to market, of course, with a product after evaluation, you would probably get in there and start editing things. You're not just going to take the example exactly as it is because it's not doing exactly what you want. So you would then use the drivers and you would tailor it specifically to your application. So what I'm doing here is this is exactly the code we just looked at. I haven't changed that at all. But now what I've done is created another task here, which is managing the CDC virtual COM port. What I could have done is just take that CDC code exactly as it was and create a task using it, run it, and then you would have both pieces of functionality running at the same time. You would have the echo server and you would have I'd be able to open up that terminal program, type characters and see them being echoed back. But in a real application, I'm going to want to do more than that. So what I've done here is take the setup. So I've taken that LPC Expresso project that we looked at first, which configured the ROMmed version of the USB driver. And I've taken all that setup code, I haven't changed any of it, and I've just put it in this function here called setup USB. And then I'm registering some command line commands, and then I'm going to sit in a loop here. And this is reading characters from the virtual COM port. If it's an end of line character, in other words, someone's typed in something and hit enter, it passes it to the command line interpreter. Down here says process command, and then it uses the virtual COM driver to write that back out again. So now we should have both pieces of functionality combined, but I've just developed it a bit further, so I'm actually using it for something real rather than just as an example. So I run that now. So there we have Echo server still running. And then let's expand that a bit. Our virtual COM port is still there, which is good. And hit enter. And now I've just hit enter, and you can see we've got the command line interface up. So very, very easily, I've taken the drivers that LPCOpen has, and I've put them to use without almost. I've thought about my own application, what I'm doing with the characters that are received, but I've put no thought whatsoever into actually how I'm going to write that driver and how I'm going to get that information. Again, when you are going to production, you may want to optimize the driver, make it do more specifically what you want, but at least you've started there with something which is already working without thinking about it. And in here, if I type help, we can see a list of commands that I've registered. Well, just by way of example, this command here shows all the tasks that are running, shows their priority, shows the stack high watermark. The smaller the number here, the closer it's come to overflowing its stack. And there is a way of trapping stack overflow in FreeRTOS. One of the most common things is a stack overflow. So if you turn that feature on, then it will tell you if you overflow your stack, so you can tune it. Obviously, if you put that kind of functionality in, it does slow things down a bit. You don't get processing for free. Run time. Right, that's what I wanted to show you. This is the interesting bit. Right, here's our virtual COM port task, CDC task, and this is the piece of the TCP task that's doing some polling. You can see there are other TCP threads there as well, but they're not doing anything. The interesting thing here is the percentage of CPU time each thread is taking. Basically, they're taking 50% each. And that's because all we've done is put them both. We've taken two Superloop programs and we've put them into the same application. And we're creating both those tasks of the same priority. So what's happening is the scheduler is running one for a fixed period, then running the other for a fixed period, then going back to the first one for a fixed period, because they're both the same priority. So that's not very efficient. Come back to here, and this is effectively what we've done now. So this is our execution pattern. Here's our COM task, is the CDC task. This is the TCP task. I've not shown the other TCP tasks because they weren't doing anything anyway. And we're running one, we're switching to the other, running that, switching back, running that, switching back to the top one, and running that. So this is what we call time slicing. Incidentally, you can turn time slicing off, but you have to know what you're doing if you do that, because you don't want to accidentally prevent one task from running all the time. So by default, time slicing is on. There's a couple of things to notice here. One is the idle task is never running anymore. The idle task is created automatically by the kernel. So when you start the kernel, it creates the idle task, and the idle task will run if there are no application tasks wanting to run. We've also introduced here that these lines going down are when periodic interrupts occur. So most schedulers will have a periodic, what's called a tick interrupt. Later on, I'll show you that we can actually turn that off. So in addition to our tasks running, we have the scheduler running. So the task runs up until the next tick interrupt. The scheduler runs very quickly to decide which task is going to run next. that task runs, okay, an interrupt came in, so the interrupt's always going to be taken. And then the task carries on. Scheduler runs again, decides this task's going to run. Scheduler runs again, decides this task's going to run, and so on. So we can see now that we very easily put functionality together, but we've done it in a very unintelligent way. So what we need to do is make it a lot more efficient now. So we're going to come back to here and stop that running. Excuse me sitting down a second. In this function here, okay, we're setting up the USB, registering commands. That's only done once. But then this for loop is effectively our, the loop which is running forever. But unless there's something to read here, there's no point. There's nothing to do unless there's actually a character to process. So what I want to do is use the kernel features to say, make this task stop running until there's something to do. And to do that, I'm going to introduce this semaphore here. If there's time at the end, which I doubt very much, because there's only 15 minutes left, then in fact I'm supposed to stop now, but there's supposed to be question time now, but I'll carry on. We're nearly at the end of what I wanted to say. We will, I could discuss that. There is resources on the web and that sort of thing I can show you. So what I'm going to do is uncomment that line there. And if I go up to the interrupt service routine up here, you'll see that when that interrupt comes in, it's giving that semaphore. So when the interrupt comes in, it says to the kernel, there's something to do now. Wake that task up so it can do it. Likewise, if we come to here, in the TCP task, again, I've done this very crudely, okay? There's much better ways of doing it. I'm just going to say if there's nothing to do, then sleep for half a second, okay? You could do the same thing, right? You could use a semaphore here as well, but I've just done it crudely. And then we're going to build that. Let that run. I'll demonstrate very quickly that both things are still running, and then we'll look at the execution pattern of that. Right. So go. Ping. Still pinging. Good. And go to the virtual COM port. New connection. COM30. COM port's still running, okay? But what have we just done? So we've taken that execution pattern and we've turned it into that. So now you see, in this example, the echo task had something to do. Maybe I typed ping or something like that during this execution pattern. The COM port task had nothing to do. So it does, in this time frame that's shown on this diagram, which is obviously just a subset of the runtime, that task never runs at all. On every tick interrupt, we still have the scheduler running. The echo task isn't doing anything. An interrupt comes in, and suddenly there's something for the echo task to do. So from that interrupt, after that interrupt, the scheduler runs a little bit again, says, oh, there's something to do there now. That task runs until it's finished, effectively tells the scheduler it's finished by blocking on the semaphore or whatever. It doesn't explicitly tell it, it just blocks on an event. And the scheduler then drops down here again. So you can see now that what we've done is, firstly I showed you how we can combine stuff very easily. Now I'm showing you how you can get a lot more functionality in a much easier way on the same processor. Because everything here, this black line is running, is free time. Before, all the time was consumed. I said before that you could turn the ticks off One of the low power features in FreeRTOS is the ability to run Tickless. So what you can do in the idle task very easily is just put the processor into a low power mode. But you need to keep the clock running, so the low power you can achieve is limited by needing to keep the clock running. It's also limited by the fact that you have to wake up periodically to process the tick. So if you watch the graph very closely on the next slide, it's almost the same, right? But these red things will disappear. So you get an execution pattern like that. Now you can go into very, very deep sleep down here, and you're not periodically waking. So there's another benefit that you've got is very easy power-saving functionality. Okay, what I wanted to show you quickly in here, some of the information that we were looking at through the command line interface. If I step that. In LPC Expresso, there are actually these plugins. This is the task table. There's a queue semaphore one and a software timers one as well. But it does show you the tasks that are there, their priority, some useful information, the state they're in. Note that all the tasks are blocked now because none of them are running. There's nothing to do. And then the percentage of runtime. So now you can see that whereas before, the CDC and the TCP were taking 50% each. Now the idle task is taking 99.5%. So you've got 99.5% free time doing exactly the same as we started with. Okay, just to finish off then we've got 10 minutes for questions if we want. FreeRTOS website, it's not a beautiful thing, right? It's an engineering site. The thing I want to highlight up there is the quick start guide. That is the first thing to look at because it tells you how to navigate the site, right? Admittedly, it's not that easy. There's a lot of information there. You need to know where to look for it. So start there and it'll hopefully tell you. Of course, the place most people start is the download link, right? Demo projects, API references on there as well. There is a PDF manual, which we would encourage you to buy, obviously, but it's on the website as well. Just to show you how simple some of these things are, there's only really 4 source files. There's list, queue, and tasks.c. That's it. They're the ones you have to have. Oh, and a port layer, which on this is GCC ARM Cortex-M3. There is a timers.c, which is optional. In version 8, which was released recently, there's also an event groups.c, or I can't remember what the file's called, but it implements event groups. But you only actually need those 3. Yeah, there's a page about running on Cortex-M. The thing that people fall over is the interrupts on Cortex-M work the opposite way round to you imagine. FreeRTOS has a full interrupt nesting model, so you do have to make sure you get your interrupt priority set correctly. There is an assert, config assert. In the later versions, if you define that, it will automatically tell you if you get it wrong. And if you look at the quick start guide, it will tell you to do that, or it doesn't tell you to do anything. It suggests you do that. So that's one of the things that will help you immensely. The way a task looks, okay, it's a void function. It takes a single parameter. It's a void star parameter, so you can pass in what you like. Normally it's a forever loop. What you cannot do is just drop off the end of the function. If you do that in a debug build, it will generate, and you have assert called, it will generate an assert to tell you that's what you've done, and you shouldn't have done it. If you want to exit the function, you just call this task delete function, okay? And you pass in the handle of the task. If you pass in null, it means delete me, delete the calling task. It's just showing you how to do periodic functions. So you'll delay until a time. So if you want to do something in a periodic way, that's how you would structure it. Creating a task, again, hopefully, this is actually the most complex, but hopefully it's simpler than our competitors. So a task is the name of the function. There's a text description. When we looked at the plugin in the IDE, and when we looked at the command line interface, you can see where the text description is useful. The kernel doesn't use it at all. Okay, it's purely there to help you. The stack size, a parameter you want to pass in, the priority of the task, and if you want, you can get a handle to the task out. So we saw the task delete. If you wanted to delete another task, you would need to know that task's handle. And did I mention there was a book? I'm afraid we're out of time. I hope that was worthwhile.